Hello, everybody. This is the review, so you'll see the black screen, and hopefully the wording will come up. It appears to be doing so now. So this is the review for exam 3. I'll send you the email with the instructions on how it's deployed. I'm sure you've all done the Blackboard exams, so there's no big mystery with regard to that whatsoever. So here we go. So the topics are mostly immune system, some I think some blood vessels and some respiratory. 55 questions for your pleasure. So the immune system we start with, again, the distinction is innate versus adaptive, and the two levels of the innate. So the outer level is barriers, all the types of stuff that's part of those barriers that are there. So whether it's remember it's basically physical, chemical, and biological. Physical skin lining, uh, biological, any of the organisms that are inevitably on top of it are sort of like are occupying space. And then the other things, secretions, skin oils and salt and acidity and those kinds of things that are there, IgA, all of that type of stuff, uh, all the components of saliva, all of those are types of things that are inherently, and understand they have to be immunological in nature. Something can be, I suppose your fingernails could be a defense, but typically they're not part of immunological defense, if you want to think of it that way. Okay. Inevitably, the secretions associated with the skin are acidic in nature. What happens is we break down cells, and enzymatically, as they deteriorate, remember what the membrane is made of. It's made of a phospholipid bilayer. So, as those effectively the lipid components separate and break down, what we're left with is fatty acids. Because remember, that's the component, triglycerides basically being a major component of that. And eventually they become diglycerides with the phosphate group, etc. So that's typically what you see associated with them. When you're looking at cellular elements, surely, I mean, we've gone over all the white blood cells, and you probably wouldn't hurt to do them again. But the linchpin when it comes to what it does to fight infections are macrophages. Macrophages are the cleanup squad. Every time something is attacked by either your innate or immune system, effectively it's tagged, marked, broken down in such a way that the macrophages are able to effectively utilize phagocytosis for all of that. The other components work separately. The antibodies work in one way, the T cells, the cytotoxic T cells work in another way, but inevitably, whatever debris is there, that's where the macrophages come in. And of course, particles and other inanimate things certainly play a role. Where do they come from? Like all white blood cells, they come from the bloodstream. Not all of them change. Neutrophils, eosinophils, lymphocytes effectively don't change a whole lot. Lymphocytes being the exception, because depending on what their line is and when they mature, they're going to become either the CD4, CD8, etc. markers when they become activated. But the ones that actually morph as they leave the bloodstream are the monocytes, which effectively become macrophages, though some stay as monocytes, and certainly the basophils, which then some stay at basophils to be fair, but really a lot of them morph into mast cells, that a cluster of granules, and the granules rich in histamine and sometimes heparin and other chemicals are all part of it. So I think that's really an important part about it. So typically you see they're very unique, the role that because of their participation in allergies, and that typically triggers them. That association with IgE is really the allergy mediator, and when you create that hapten protein interface, that hapten or half antigen, then becoming the complete antigen, now voila, when they bond to the free arms or the variable arms of the IgE that protrude from the mast cell, they induce the release of, typically, at the very least, histamine and sometimes heparin. And those are the ones that particularly provoke shock type reactions because they're anticoagulant in nature. The histamine dilates the blood vessel, so we're preventing clotting. And sometimes there's other chemical factors that are in there. They're not the same kinds of factors that you would see in other systems. The interleukin systems are part of the adaptive system. This is not necessarily part of the adaptive system. Things like prostaglandins are separate. They're localized mediators, not generalized mediators. So there's a lot of nuances between them. You've got to understand. Some agents work locally. When we begin to look at paracrines or autocrines, those are agents that work locally. Icosanoids, which become paracrine type agents or local mediators, are things that prostaglandins are part of. And so that's one area that you have to be cognizant of. When you look at antibodies, for the most part, they circulate throughout the system. Sometimes the particular cell they're adherent to or part of. Okay, so where do they go? And what do they do? And what are the distinctions between them? So, what happens when, let's say, we do have the activation of some of these chemicals? And most of them, remember what the first two things are. When your immune system is activated, okay, inevitably it starts trying to provoke some kind of inflammatory response. And it starts with cytokines or chemical agents that are going to dilate blood vessels and increase blood flow to the area. You're basically bringing in troops to fight whatever is going on. So you have lots of white blood cells. The fluid typically dilutes some of the toxins that are there. You're going to have a variety of factors in the blood that act. That will be clotting factors. All of those types of things are part of it that are there. What does it effectively do? What do we see as a result of it? We see warmth and swelling, increased blood flow, and that dilation of blood vessels tends to lead to both swelling and warmth that's associated with there. So after that, we begin to get pain, and sometimes fever will be associated with it. Sometimes, swelling will be associated with it. All of those types of things. So increased blood flow, redness and warmth, I think would be fair to be first, and then pain and swelling would be afterwards. Those are the cardinal signs of inflammation. Classically, when we used the Latin, which was the language of medicine for the longest time, rubor, calor, dolor, tumor. Redness, heat, pain, swelling were all part of it. Those were really this whole lack of function thing that they put in. I don't necessarily agree with that are there. A word about immunoglobulins. Remember, first one on the scene, IgM. When we have the adaptive response, that's the initial, and we can even titrate or look at those things. Uh, from a standpoint of analyzing a sample and maybe undergoing some degree of electrophoresis or fractionation or other means to identify it. If IgM is up there to a particular infection, we know it's in the acute or early stages. If it's IgG, we know we're in the later stages that are there. IgM first, IgG second, and IgG in vast numbers. And I know for some of you, this hopefully there'll be a certain degree of review or restating things that you might have gotten in immunology. So obviously for those not taking it, it's a little bit of a disadvantage, but it shouldn't be a major disadvantage because I think we're covering everything quite thoroughly. What happens? What are one of those innate chemical defenses against viruses? Interferons. Yes, we make more advanced ones in the adaptive system that you noted. And I don't go into all the specifics of the different types of interferons. I just call them interferons for the time being. What do? They're a protein agent that's released by a cell that's been infected by a virus that sends basically protein-based signals called interferons to other cells in the neighborhood, basically saying, hey, there's a virus. Obviously, that text alert system that they have isn't working as effectively, so they use chemicals. Just the same thing when we get one of those beeps from our phone about trees are down on campus or there's a power outage. Basically, they're saying the same thing, except chemically what they're doing is they're making it more difficult for the viruses to attach. The resultant effects of the activation, particularly of your secondary immune system, and I'll give you an idea as I'm doing this at home, and there's somebody whose nose is right next to me. If he starts to make noise, we will do this in segments because he'll insist on making a trip outside, or he'll annoy the kitties. Okay, so he's doing the slide across the floor maneuver with his rear end. That usually signals there could be a possibility of going out, or because he was just out. But I digress. So the interferons effectively what they are, they're part of that innate system. And what the other thing that the cellular arm and all of those cytokines, what they lead to more than anything else, is the way it's basically our body indicating it's ramped up, just try to fight things without having to bring in the adaptive system. That's inflammation. Sometimes it gets out of control. And when the inflammation gets out of control, it can cause a problem because if there's an overabundance of these, if the fever is excessively high, if there's some problem associated with our immune system, more along the lines where it works inappropriately as opposed to being immunosuppressed where it doesn't work well at all. So, what does fever do in a mild to moderate sense? What does it do? It basically increases metabolic rate, it increases your defense mechanisms, it increases enzymatic reactions, it creates overall metabolic and cellular activity. And so, what is it related to? Chemicals that different kinds of infections or conditions that release, which are referred to as pyrogens. Pyro for fire and generating, so it's pretty self explanatory what it is. And it can happen with bacteria, it can happen with viruses, it can happen with protozoans. It doesn't matter. Okay. Anything that's doing it. I mean, we mistakenly think, well, it's viral. It shouldn't. I mean, viruses, common cold isn't generally pyrogenic. It's a little bit different. The immunology works differently. But if you have an adenovirus rather than the typical rhinovirus or the common cold, then we begin to see pyrogens. So it depends on the virus and what it provokes and all those things. Which brings us to what happens if those innate defenses don't work. If they don't work, now you're into this very aggressive, powerful, system wide adaptive system. It has immunological memory, so it's useful for going forward. It works at the area of the infection, but it sends chemicals or messengers or cells all over the body. Most of the time, the activation is in lymphatic structures, mostly in the lymph nodes. And inevitably, if we're getting to this stage of things where it's gotten past the innate, now the linchpin for this are T cells. So the T cells get their name because their activation or their maturation is a better word is from the thymus, hence they get their name, and it depends on what markers we carried. And we went over the CD4 and CD8, and we'll look at that again, which sort of predicts, if you will, what kind of cell line is going to be. Is it going to be a helper T cell? Is it going to be a killer or cytotoxic T cell? Those kinds of things are what develop. It's a little bit different. Again, I commented before when we're talking about allergies or these haptens or half antigens, they're incomplete. They're not large enough to be able to generate an immunological response. They have to bond to something. Now, depending on what they bond to, most of the time it's localized and adapted and it's innate as opposed to adaptive, but it could conceivably be adaptive. Okay. So I think that's kind of the thing that you have to use. And that the term hap10 means half antigen. The dog's getting into stuff he shouldn't. And so it's a very, very specific term that's there. And typically they have to bond with the protein. When you're talking about other things that are part of antigenic science are things like epitopes or determinants, which are about the same. That's the specific marker that's typically displayed on MHC1s and MHC2s. You can't have that in a bag of pins. Safety pins. You're in trouble. No, he's taking my chair. No one likes the dog. So, I mean, so this is again an exam that deals with a fair amount of terminology, and that's part of it. What do antigens do? Okay, an antigen got its name originally from being antibody generating. What does it do? It sends out signals to our immune system. So we're talking about foreign or unrecognized antigens. Okay. Typically, if we're going to have an immunological response, the other kinds of antigens that don't have that, okay, that are self antigens, typically are associated with these MHC complexes. Self cells, MHC, major histocompatibility, is what the big H stands for. And compatibility means it's compatible with tissue. So those MHC complexes, so MHC1s and MHC2s are part of that. It's when those complexes display something foreign, like a foreign epitope or determinant that it provokes the activity of the adaptive immune system. So normally we look at these MHC markers to see if they're regular or irregular, and particularly when we're doing things called tissue typing. Tissue typing is when is somebody a compatible donor for, let's say, a kidney. We examine these self markers, and let's say arbitrarily there's 100, and if you have 75 that are similar to the person who needs it, you probably qualify because you can sort of gauge the immunological response based on this. And I'm just sort of talking off the top of my head that are there. I don't know what the exact number is, and I don't know which ones specifically, but that's what tissue banks and I don't know if they use the same term. They used to call it the core, which was CORE. I don't know what the acronym stands for at UPMC. That had to do with where they stored this type of data for transplants when they were, because they've always been a transplant center. So T cells are a very specific cell to be activated. And there's a lot that goes on, whether it's CD4 or CD8 cell, and you have all that positive and negative selection. And so a great many of those cells don't meet the criteria and undergo apoptosis in some way, shape, or form as they're trying to develop. The effectively only about 2% of all the T cells that are generated in the bone marrow of the lymph cells that are going to become T cells, rather, are actually able to become effectively to become T cells. They're assisted by another cell that's really, even though it's associated with your adaptive system, it's effectively part of your innate system. It's one of the cellular. They're called antigen presenting cells. Antigen presenting cells are everywhere. They're in lymphatic structures. They're in areas where you're exposed, whether they're in the skin or gastrointestinally or in the liver. There are all sorts of things. We have Kupffer cells and dendritic cells, and those cells are samplers. And they sample foreign entities and they sample normal entities. When they sample normal entities, they're basically showing them to your immune system to sort of keep it in tune. So basically, to keep it activated and constantly checking the environment and responding to things that should be responded to or not. On the other side of things, if it's something that's foreign, then they really are significant because it will it will indicate, basically the marker that it will come up with will require a response. So collectively, we call them antigen presenting cells. And so, what happens when we have that process? It's an antigen presenting cell. It's picked up a marker, whatever the marker is. Let's say it's a marker that's on an MHC2, and we're going to start generating a B cell line. That B cell line is going to generate, we call it clonal selection. It's going to start to clone a vast number of cells. The vast majority of that vast number of cells are going to become antibody producers. They're the actual arm, the effector cell, as it's referred to. A small percentage, but an important percentage, are going to become memory cells and encode that information so it can ramp up production right away to IgG levels and very, very quickly. There's none of this 6, 10, 14-day lag period, starting with IgM and then IgG. If you remember that graph that we took a look at, the plasma cell is the effector cell. They are effectively morph into massive antibody generating cells. They look a little bit like the typical lymphocytes, but there's a greater amount of more visible under electron microscope rough endoplasmic reticulum, because they're all making proteins to be excreted in vast numbers. What we do is a similar process to create these when we generate various kinds of vaccines that are effective. And it requires a process known as attenuation. When you attenuate, you alter, but you don't destroy, if you want to think of it that way. When we do tetanus or diphtheria, this classic DTaP, diphtheria, tetanus, and acellular pertussis, those are toxins. They're protein-based toxins. We attenuate them with heat. We destroy their toxicity, but we preserve their antigenicity. So they'll provoke an immune response without provoking damage. When we do the same thing with various kinds of viruses, we attenuate them. So when we're doing MMR, measles, mumps, and rubella, we've altered that virus enough so the virus will still generate antibodies, but you won't have the destructive aspect and the potentially lethal aspect of whatever viruses are involved that are there. Again, the COVID-based immunization is different. It doesn't really attenuate so much as what it's done is it's analyzed. It's basically constructed the antibody from an mRNA model. So basically, they've created the messenger RNA sequence in the laboratory and taken that messenger RNA sequence, constructed it, inserted it into some type of arm that will cause that change in our cells. So attenuation, if you wanted to just summarize, inactivates the viruses, but it keeps them antigenic. There's different ways to do that. COVID, I think, is a little bit different in that way. Certainly, it's causing an antibody production that's going to inactivate the virus and take care of it down the road. So that is artificial acquired that's artificially acquired active immunity made in the laboratory. For someone like me who got the measles, that's naturally occurring active immunity because I got the disease and I have the immunity. Passive immunity means you can get it passively, naturally from your mom during the birth process or during nursing by way of lactation or lactated products versus receiving transiently antibodies from your mom, same kind of a thing, naturally acquired passive immunities that you receive in utero versus getting an antitoxin for something. Let's say if someone has had an episode of a snake bite would be a good example. We administer the antitoxin. Someone gets tetanus and they weren't tetanus immunized. If you get to that antitoxin fast enough, you got a shot to take care of it. So the fetus is more passive acquired immunity, but it's naturally occurring. And antibodies themselves, as we understand the two pairs of polypeptide chains, the heavy pair and the light pair, the combination one side when they bond together in that classic formation, that letter T or letter Y kind of formation. You have the constant end, which really is the type of antibody, and the variable end, which is shaped and modified to interact with the appropriate determinant or epitope. And that's there. The large one is IgM, and typically, even though they all start as monomers, that one tends to form a pentamer, very useful for agglutination. IgG is the most abundant, does most of the hard work when it comes to dealing with long-term immunity or immunological memory, as well as fighting the active portion of disease. IgA and secretion, IgD, still don't know. IgE about allergies. And all the things, the way antibodies work. How do antibodies work? They work in a lot of ways. They don't perform phagocytosis. They tag things, whether they neutralize them, whether they fix complement, whether they agglutinate, whether they precipitate, whatever they do in some way to make that combination of the antigen or the antigen carrying agent more able to be identified and gobbled up eventually by macrophages. Well, I like to say, so they basically tag it, and then the macrophages can come along and destroy it. That's really the first unit of this. I'll come back and do the next unit, so we'll call this part 1, and then we'll start the next part, which is going to be more about the T cell based line. I think that's a good part of it in some aspects of some of the reactions that are there, a little bit more specifics, and something about hypersensitivity, and then we'll move on. So basically, if I'm going to summarize, okay, the first, I would say, for your studying purposes, the immune questions are going to take up more than half. So if there's 55 questions, about 30 to 34 or 35 of those questions are going to be immunologic. That's what you study the most. And then the other ones, the respiratory and the other physiology, the blood vessel physiology, will be the remainder of the exam. So we'll stop it there, and I will come back and pick it up where we left off.